we will have today's lecture in the FEA and constitutive modeling in geomechanics course on FEM in geotechnical applications. So, first question we have to answer here is how to handle a geotechnical problem before going into the application in FE. So, as you can see, the first one will be to analyze the ground. So, you have to acquire land, then reconnaissance of the site. You have to understand the geological history, the formations, then detailed survey and the leveling. So, overall genesis of the site has to be done. Then next one is come that the very important step, how the soil is soil behavior is happening, like what should be the ideal schedule for the soil testing, what are the different types of tests you should do, field or laboratory in entire spectrum of the soil investigation. Then with all this input you have to go to the modeling. Now, modeling can be different types. One of course is the physical modeling, which is not always possible because you cannot every time create a model to test it and before execution. Then you can do the analytical, which is obviously the preferred one. However, the problem is for difficult complex problem, it will be extremely difficult to come up with an analytical model. So, that is where comes the final one, the numerical analysis, which can be finite element, bending, finite element, boundary element, finite difference and so on. Now, the particularly these numerical tools are very effective in a sense. They may not be the 100% accurate, but however, they can handle complex situations and relatively easier and within the time frame given for a particular project. So, there are 4 players: user, programmer, analyst and the engineer in any of this kind of finite element modeling. So, what are some common geotechnical analysis softwares which we generally see? The most popular, there are many more. I am just listing some of the most popular ones. We start with Plexis, which is a finite element based software. Is one of the most popular because it is extremely user friendly and it has certain number of geotechnical features like anchors, geogrids, tunnels inbuilt, so that you can just simply click and play. There is no, it is not a general purpose, it is meant to be the geotechnical applications. So, that is why it has various types of constitutive models for which is suitable for the soil. However, there are certain limitations of Plexis. One of the major limitation it's they call so-called the black box type software. That means it's so easy to use that the person which is not properly trained in geotechnical engineering may possibly run a Plexis analysis by simply following some steps. However, he or she may not be able to understand whether the results, whether the analysis forms which are coming are accurate enough to be used in practice. Some of the technical issues related that like some of the non-conventional geotechnical problems which we are everyday facing nowadays is such as large deformations, irregular geometries. It's little bit of difficult in nature. So, in short, the flexibility which is the essence of this kind of modeling is not so much there in Plexis. So, next one in the line is FLAC, which is a basically finite difference based software, finite difference based package, and it can be used for particularly the complex geometries with the dynamic loading. It also has, like Plexis, it also has certain structural elements which are very good anchors, piles, rock bolts. It is very popular for rock mechanics applications as well, when if you want to do a complete rock model. However, the limitations are it is not as simple as Plexis. So, you need to know a bit more than what you expect to know for the Plexis. It is extremely difficult to model complicated geometries dynamic analysis may sometimes encounter convergence problem. Then comes the GeoStudio, which is not a single software, it is a collection of various softwares, and it's principally they are based on the limit equilibrium type of approach. This class of softwares having wide variety of applications, packages meant to be for geotechnical or geoenvironmental usage, such as SlopeW is for slope stability, SIPW is for seepage problems. There are something called dynamic analysis, it's a SCOIC-W, TEM-W is for geothermal models, and so on. One of the major limitation is the solution sometimes overestimates the soil strength. It is not suitable for complicated geometries. There are couple of general purpose finite element packages are there, such as Abacus is one of them. It is, as I said, it's a general purpose, so it is quite flexible in nature. However, it is not so much useful. I mean, it's not that people can simply plug and play type. It's you have to really learn a lot inside of the finite element to able to use this variety of software such as Abacus. It can model solid and water as two phases, so that's one of the major things. So it's you can do effective stress analysis, but one of the drawback of Abacus is where the memory, runtime memory, if you require more, then sometimes Abacus analysis are not so efficient in terms of the running time and the computational cost. So that's one of the reason why Abacus is not so popular in industry. The other one is the ANSYS. This is also a general purpose finite element package. It is quite efficient again in dynamic analysis. Compared to geotechnical side, ANSYS is more suitable in structural engineering in certain areas, because there are lot of requirements for geotechnical analysis which it's not there in ANSYS. There are few more very specialist application type softwares. One of them is SASI, is meant for soil structure interaction analysis. LS Diana, which is particularly suited for someone is working in the blast loadings. SECH-CRISP, which is one of the earlier version of the software where finite element package where couple flow analysis can be done. There are many more, and there are so much development is going on every day. So you expect that for a specific problem you will also have a specified package. So in summary, modern finite element softwares are generally very easy. They are scaled based on the ease of use, how easy to use it, but that doesn't necessarily mean that ability to use. So that's where we have to draw a balance. It's a ease of use to the ability to use. So there should be a balance. Otherwise, this is particularly true for geotechnical engineering. Otherwise, you will have this kind of consequences, which is maybe a simple mistake, but consequence is long term. So let us see some of the example where we can use finite element this type of analysis to study the geotechnical problems. We start with a simple one where we will analyze slope stability problem. So this is a typical slope which we use in for any kind of embankment purpose. It can be like ash pond type of thing. So basically this is a ash pond. You can see there is a ash core, and this is earthen embankment. So this was the actual earthen embankment, starter dike as we call it, and then we have the fly ash getting stored in this kind of areas, and as we cross the initial embankment, we need to raise the height of the this particular dike. So, how it's raised? It's the again inside we fill up with the ash. So, this is again the ash. However, this is the outside there is a clay cover. So, that you do not want your ash to fly around and it's not cause any environmental issue. So, this is actual dike in one of the aluminum company industry ash dike. So, we did the analysis in Plaxis. As you can see that it has been done in when then the latest version of the Plaxis, and then it is a plane strain model with 15 noded triangular elements. The base of the embankment is assumed as the fixed base. The sides are horizontally restrained. We have taken that one of the major issue of finite element is how to decide that the width of this model, this dimension. So, there are certain rules are there, but I would say that it is more like we have to do a sensitivity analysis to understand how big or what should be the preferred width of the model. You have to do a trial and error method to fix up these boundaries. So, we got actual soil data, soil and the fly ash properties from the test done at the site. So, we use that. So, we incorporated the material sets in Plaxis. So, we have ash core 1, 2, 3, there are 3 levels of raisings, and then the earthen cover, original soil, and then the foundation soil, and then we have given the input properties. So, then we went for the calculation stages. We did the plastic analysis. We allow the soil and the ash to deform in plastically manner, followed by this phi C reduction. This phi C reduction is basically the stability analysis. That means, what in Plaxis the program will do is they will forcefully reduce the C and phi of the soil property. So, as the C and phi soil property reduces, they will see at which point of mobilized cohesion and the friction the failure happens. So, the ratio of mobilized to the original strength properties will give you the factor of safety. So, either they call it a safety analysis or a phi C reduction. So, name itself suggests that we are reducing the shear strength of the soil. So, that is where the factor of safety develops in the cumulative multipliers. So, we can actually see the slip circle. So, here this contour will tell that when is the critical failure circle. So, you have to choose the total increments contour plot, and then you will see the failure surface. So, you have to keep in mind that this is kind of a representative of the slip circle, but principally it is not the actual conventional slip circle which we generally do for Bishop's method or similar liquid equilibrium method. This gives you the failure. I would say that this can be considered as the part of the embankment which is getting fell or which is getting plastic mobilization happen. But despite that, you can have an idea that where your slip is actually bound to occur. It may not be exact matching with the limit equilibrium, but it will give a indication. So, this is a simple exercise for the slope stability. Usually, the general understanding is that the factor of safety which you obtain from the finite element analysis for a slope is generally slightly more conservative side compared to the factor of safety which you obtain from the limit equilibrium approach, like your Bishop's method, your Jan-Bu's method, or Morgenstern-Price approach, and so on. So, the next problem which I want to discuss here is slightly more complicated in terms of the analysis. It is the analysis of excavation and a support system. So, as you can see, this is a excavation site in a extremely congested area. It is extremely congested urban area where we are going to do a excavation. So, the excavation carried up to a depth of 11 meter from ground surface, because topsoil was a kind of a soft clay. So, you have to cross that soft clay, and you have to put to have a support system for that. It is quite a large plan dimension for the excavation, 100 meter by 26 meter. The excavation area was circumferenced by a 5-story building on the north side, roads on all other sides. So, again, as I said earlier, it's a very congested urban environment. So, the sheet piles were first driven to a depth of 30 meter below the ground surface to support the excavation. As I said, the top layer is a soft clay, so you have to really go deeper to get a proper anchoring of the sheet pile. There are 6 levels of internal struts. So, you have a strutted excavation at 3 different sizes. On top of that, there will be a steel piles driven down the bedrock, because at the excavation floor you have a slab to be cast, but that slab the soil is not good enough to support that slab. So, you really have to have a piles supported slab at the excavated level. So, this is typically the case. So, as you can see, this is the excavation depth of 11 meter, and this is the slab which is supported by this H piles. So, what should be the step of the or stages of construction? So, I just explain the stages, then we will go back to the soil properties. So, we have to first install the pile installation. So, we just simply insert hammer in the H piles. Of course, later we will cut it up to the excavation level, then we will drive the sheet piles, then we do the excavation up to minus 1.4 meter, then we install the strut and preload it, and then similar thing we repeated up to the up to the 6 meter, where strut 1, strut 2 and strut 3 installed. As you can notice that the preloading amount increased. Again, these are the thing data came from the actual site. Preloading increased because to control the preloading of the strut increased to control the deflection of the sheet piles, and then beyond 7.5 meter you simply install. One of the major issue here is for each stage you have to have a lowering of groundwater table. So, that accompanied with this cutting. So, we will discuss that also. So, if you see the soil profiles, so there are explained with this itself. So, there is a thick layer of marine clay, and then there is a silty clay which is not bad in terms of strength. There is a medium stiff clay which is good, which is slightly over consolidated, followed by sandy silt, and almost close to 45 meter you will have the weathered rock starting. So, these H piles are resting on the surface of that weathered rock. So, excavation is 11 meter, that means excavation done within the marine clay itself. So, that is why you need so many different levels of strut. So, as you can see again in the stages that we have 6 levels of strut, but only top 3 level we need preloading to control the pile, the sheet pile deflection. So, this is the different strut locations with different strut sections. So, as I said, the initial position of the groundwater table, it's almost at the ground, it's a coastal area. So, we can take it as a ground, and then each excavation stage the groundwater table lowered. So, we call it typical as Z type arrangement. So, that means you have this, so you excavate up to this, initially groundwater table is like this. So, once you have the excavation up to this, so you lower the groundwater table like this. So, it is like a kind of staggered arrangement. Then you go to the next step. So, you further lower the groundwater table this. So, that is how we model, and that is how it will be exercised in the field as well. So, this is a typical property set which came from the soil investigation. Please remember this question. So, we will come back with this. The type is drain and undrain type of analysis. which we will discuss very shortly. So, this is the structural properties of the sheet pile, H piles and the struts. Essentially the struts are axial members. So, we have given the axial rigidity. Sheet piles and H piles we have given both axial rigidity as well as the flexural rigidity. So, this is the typical results obtained. As you can see, we have the lateral deflection, bending moment and the vertical settlement. Lateral deflection is, and for this each dotted line represents that how we monitor the deflection for each excavation stage and after installation of the strut. So, we can see that lateral deflection gradually increases and maximum after stage 6, that means when we reach the excavation of 11 meter, so 11 meter is somewhere here. So, you are getting the maximum deflection slightly below the excavation depth. Same thing observed in the bending moment diagram also. You can see that it is maximum bending moment occurred some place below the, little below the excavation depth. We also measured the what is happening in the vertical ground, in the ground surface, because as I said that this is a congested environment. So, to track how the ground around the excavation is settling also is a key issue. As you can see, there is a very significant settlement of 180 mm expected at the ground level. So, now as I said that there is one of the major issue about is the type of analysis, whether drain or undrain. So, what is drain and undrain behavior? I know that this course has been discussing this drain and undrain quite a number of times. So, we will just see how this, when we use any software, how they are treating it. Now, before going into that, undrain generally excess pore pressure are not allowed to dissipate, as we all know. Drain excess pore pressure is completely dissipated. That is the simple way of looking at it. So, how to choose drain and undrain? So, undrain generally we call it short term problem, earthquakes, blast, where you are not allowing the excess pore pressure to dissipate. Long term is the excavation, tunneling and so on, because here long term performance is key issues, particularly if you talk about the cohesive material. So, in plexus you can do it in a various way. They call it method A, B and C. So, you plexus material setting should be undrained. If you choose the material model more Coulomb, then you have to, in A you have to use all the effective strength and the effective stiffness property, so that the computed stresses are effective stress and the pore pressure. In B, undrained method is where you use strength as total stress, but stiffness at effective stress. So, you get effective stress and pore pressure as the computed response. If you choose non-porous, there also you can, can do undrained analysis. So, there it's everything will be the total stress, both the total stress, stiffness, strength as well as the output. So, now we will do a simple cross check that what we said is correct or not. So, if we use the same problem, same trial problem and do it in these 3 different methods, let us study. So, this is a simple excavation problem which we just analyzed a similar line. So, for method A we used, as you remember, it should be all effective stress properties. So, we have effective strength and the effective stiffness properties. Method B, it is the effective strength, but if total it is a total effective strength and the total stiffness. So, as you can say that it is effective stress analysis. We have a delta Cu increase we have done, and then if it is method C, everything total. So, we have again used the total stress or total strength properties. So, all the for top 2 cases A and B, use the conventional way of handling water table, which I just explained. It is a Z type water table. In method C, there is no water table, it is a non-porous. So, place ferritic line at the base of the mesh, and you have the modeling of the K0 conditions. Or method A, for normally consolidated soil, you should use K0 as per the Jackie's rule 1 minus sin phi dash. For over consolidated soil, you can use K0 NC with a factor under root OCR. Method B is same as method C in terms of K0 conditions. Method C is a total stress based approach. So, here you have to consider that it is the total stress K0 condition. So, use the sigma h over sigma v, not sigma h dash over sigma v dash. So, if you use properly, you can see that the deformations are very similar. The plastic zones or the yield zones are quite close. Even the bending moment, wall deflections, bending moments, everything are coming within a reasonable values. It is not totally different, I would say. So, with this two simple plane strain problem, we will go to the problem 3, where we will study the 3-dimensional FEM, where we will study a simple response of a pile under lateral load. So, this is a 3-dimensional numerical model of a field pile lateral load test reported by Urano in Japan. The analysis was carried out in Abacus. The soil layer used as a hypoelastic soil model. Steel piles and the raft, pile group, everything, all the structural elements are considered as linear elastic material. So, this is the typical soil layer. Is a major your attention should be in this particular layer, where there is a loam and clay layer is there, which is relatively soft. So, we use 20 noded quadratic brick elements with reduced integration, then 3 noded quadratic space beam element to model the piles. This is the soil property. As I said, there is a clay layer of slightly lower strength and stiffness. Even here, both the layers having a problem. So, there will be a lateral load issue in those particular layers. So, this is the boundary conditions. So, this is hypoelastic soil model, where it's basically a nonlinear elastic type of model, where you have modulus varies with strain. So, the pile there is a challenge of modeling pile, because piles are generally modeled using the solid elements. Now, in solid elements, bending moments directly cannot be measured. So, we have to have a 3 noded quadratic space beam element inserted within the pile, and those space beam element of its flexural rigidity is scaled down by 10 to the power 6, and bending moment will be whatever the computed bending moment, we have to multiply with 10 to the power 6. Now, one should keep in mind this is possible if your structural elements are linear elastic. We assumed here it is linear elastic, so that is why we are doing. So, if it is not linear elastic, what we should do, we will have the next the final problem, there we will discuss that. So, the input load is basically a pulse load. So, it is a triangular pulse applied. So, let us see how it compares with the field experiment. So, this is the field experimental data reported by Urano, and this is the analysis, is a limit equilibrium type of analysis done by the Urano. Our Abacus analysis is somewhere falls in between the field and the Urano's analysis. As you can clearly see, Urano's is quite grossly over predicted the field, but our thing is slightly better. So, now the problem is, as I said earlier, that there is the lateral load carrying capacity was a question in this particular case. So, because this soft layer, so what it is planned by the site is like, let us have a grouted soil. So, we call it reinforcement body. So, we model that also in the Abacus, and then it is a linear elastic material we assume. So, if you put that reinforcement body, so this is the field test data. So, this analysis by Urano, again it is over predicted. However, in Abacus also it is more or less close to the analysis by Urano. There are various reasons possible. One of the major reason may be both the cases, the Abacus and the Urano's analytical model assume this reinforcement body as linear elastic, which may not be the actual case. However, one of the thing which gives us satisfaction is that the bending moment is slightly over predicted, which is from the safety point of view, it's fine. We did a bit of parametric study to see that if you change the position of the reinforcement body depending on the soil condition, whether that makes any difference. So, this is the old grout position, this is the analysis by old grout position in Abacus. However, there is no change in the bending moment, but being said and done, there is a change in the location of the maximum moment. So, it shows that the reinforcement body is giving a kind of a fixity around the pile. So, it's the bending moment development is localized to that region. One of the major advantage of getting this results is shows that you can design the pile or structural design of the pile can be done based on this. So, it can be localizedly to avoid any kind of failure. We can flexural failure, we can have additional steel. So, then we will go for the seismic analysis of a instrumented bridge support. Again, this example of a 3D FEM. This is the last example problem. So, it's instrumented bridge support. So, it is been reported by a actual earthquake response measured in Mexico City, one of the road over bridge, and the construction happened just before the 2004 Guara Coast earthquake. So, and the bridge luckily was the instrumented. So, it's recorded some interesting responses. So, it's a 405 meter long impulsora bridge, northeastern part of the Mexico City. So, it's the instrumented support 6 is the one that we will model. So, it's a box foundation and 77 RCC square friction piles of cross section 0.5 by 0.5 meter extended up to 30 meter depth. So, it's a predominantly it's a pile raft type of approach where piles are carrying 85% load, raft is 15%. So, this is the typical diagram. So, this is the Google Earth view of the impulsora bridge, and shear velocity, as we know in the Mexico City, it's a thick clay basin is there. So, top 30 meter is extremely soft clay. Now, the question about the modeling of the pile, as I said earlier, that if you are fine with modeling the pile as structure linear elastic, then there is no problem. However, if you want to have some kind of damage plasticity model type of thing, if you want to include in to model the pile to see is there any kind of damage happened, then you cannot use that indirect method. So, here what you can do is you can come up with a kind of a hybrid type of finite element modeling. So, here this is the continuum element. So, each continuum element will be connected to a central beam. So, this is my central beam element to a rigid links. Again, these rigid links can be modified later with like we can do a check whether it is rigid or flexible link is required or not. But for now we have tried like, so there is this node belongs to the continuum solid element, and this node belongs to the central beam, and this connected by the rigid link. So, this way we can have both continuum element as well as the beam without interfering each other properties. So, this is the way that bridge had been finite element mesh of the bridge pier structures. As I said, it is support number 6. So, as you can see that is a measured and the computed response at ground level. So, this is the actual at 60 meters. So, input. So, this green and blue are the basically computed response spectrum at the surface and the measure at the surface level, which is for all practical purpose we can say it is pretty close. The measurement and the computed results even closer at the raft level, we can see exact match, even at the bridge deck level also we can see exact match. So, this is today's lecture we have seen the overall description of the finite element usage of finite element softwares for a few geotechnical problems, and how from plain strain to go for the complex seismic response with the different nuances of modeling from the meshing to the properties, and how to do the drain and undrained behavior, where to use the pile, the regular pile elements, or whether you can use a hybrid type of pile elements for different purpose. For further details, you may refer of these papers, which has the detailed results of all these studies. Thank you.